Welcome to the INTAROS technical webinar on mooring operations in polar waters. My name is Agnieszka Beszczynska-Möller. I'm physical oceanographer from Institute of Oceanology, Polish Academy of Sciences in Sopot in Poland, and I have been working with oceanographic moorings in the Arctic for over 20 years. In the INTAROS project, in work package 3, which was focused on enhancing in situ observations in the Arctic, we deployed the moored array north of Svalbard in the southern Nansen Basin of the Arctic Ocean. And in this webinar, I would like to share with you some experience which was gained during these mooring operations, as well as from recoveries and deployments of other moorings in different areas of the Arctic, and also what we learned from collaborations with other projects, for example, CATEX project, also operating moorings in the Arctic Ocean. This general introduction to mooring operations in polar waters, I would like to start with introducing a mooring as a platform for long-term measurements. And I would like to discuss some environmental constraints which are important for mooring measurements in polar areas. I would like to shortly discuss different types of moorings used for applications also in the Arctic, and then show you examples of moored instrumentation which is used for physical, biogeochemical and biological observations also in polar waters. Then I would like to address briefly mooring hardware, which is a critical component of each mooring, and in particular polar moorings, and also the localization equipment, acoustic equipment, which is used to find your mooring, which is even more important in polar areas. I would like to quickly discuss the mooring design and the specific requirements for operating the moorings in ice-covered areas, and then to walk you briefly through deployment procedures and also recovery procedures and possible challenges which can be met during fieldwork in the Arctic. At the end, I would like to show shortly some current and future solutions for moored arrays in the Arctic Ocean, and wrap up this presentation with a few take-home messages about moorings in the polar areas. Oceanographic mooring is an observational platform which is attached to the bottom, usually with the Haiti anchor which sits on the bottom, with the line or rope. And there is a collection of instruments attached to this rope, and on the top there is a flotation device which keeps the line and the instrument upright in the water column. The measurements on moorings are so-called Eulerian measurements. What does it mean? Fluid properties like pressure, temperature, salinity or the ocean current are measured in a fixed location. So we are measuring how do they change at the specific position, and these changes are described as functions of space and time. Moorings are well suited for long-term observations because they stay at the same position for longer periods. Usually measurements with the instruments on moorings, they have high temporal resolution, usually from minutes to hours. But the vertical resolution of your measurements on the mooring depends on the distribution of instruments and the types of instruments and sensors that are used on the mooring. The more instruments you have, the better the vertical resolution is of your measurements. But there is also a drawback. Moorings usually have relatively low spatial resolution. There are only a very few dense moored arrays in the key areas of the world ocean. And the resolution, the spatial resolution which is needed to resolve a specific feature depends on the Rossby radius of the formation, which is the scale of ocean dynamics. So the smaller the scale is, the more moorings you need to resolve your studied process or studied feature. There are different types of oceanographic moorings used in the world ocean. The most common type of mooring is a surface mooring, which is equipped with a top buoy, large top buoy, as you can see in the middle of this schematic, which is floating on the surface. And these moorings, they can measure very close to the sea surface with the instruments which are located just below the top buoy. They can also measure, for example, surface meteorological variables with automatic weather stations, and other instruments can be also located on this large surface float, for example, for radiation measurements or other observations. The big advantage of these surface moorings is that they can telemeter the data in real time. They can send data to the land station either using a satellite link or, for example, using radio link if they are closer to the shore. These moorings are also much easier to find and recover because of this surface element. But they are also exposed to waves and winds. And because of that, there can be a very high tension on surface moorings and also unwanted motion which comes from the surface forcing. The other type of moorings which are used in the ocean are subsurface moorings, as these examples to the left and right on the schematics. The subsurface moorings also have a top float, but this top float is located below the surface, usually a few tens meters below the sea surface. And because of that, they cannot measure in the surface and subsurface layer. Unless they have a kind of profiling device. But they do not have any permanent sensors just under the surface. These moorings, subsurface moorings, are not exposed to the wind waves, and they are also protected from sea ice on the surface. They usually have smaller and lighter components, and they are easier to handle than these large surface moorings. And usually there is a less movement from winds and waves. But these subsurface moorings, they can also be pulled down by ocean currents quite significantly. And what is very important, these moorings, they have to carry acoustic releases. The devices which would allow to release the mooring from the anchor before it is recovered. I will come back to this point a little bit later. And the last type of moorings, which is not shown on the schematics, are bottom moorings. Simply, those are structures like frames or landers, which are sitting on the ocean bottom, and they are usually used for measurements in the near bottom layer. They can be also used for example, for acoustic measurements, which measure remotely in the water column. Let me quickly discuss environmental constraints for mooring operations in polar waters. As I already mentioned before, the main factor is sea ice. The sea ice coverage, which is prohibiting navigation, that means you cannot go to these areas without icebreaker or at least ice-strengthened ship. The sea ice on the sea surface also prohibits the surface access. These drifting icebergs, drifting sea ice with the large ice flows, they virtually do not allow any kind of surface float, which could be used, for example, for telemetering your data in the real time. Operations in polar areas are generally very difficult because of challenging weather, severe storms, extremely low temperatures, clouds, and very often fog, which makes any kind of operation on deck more challenging than in the other areas of the Arctic, of the world ocean. It's very often these operations, they have to take place during polar night. Which means operating in darkness. The polar night lasts nearly half a year, and operations which take place in spring or in late autumn, usually they are done in dark conditions. These areas are very remote. There is no regular ship traffic. There is a very difficult logistics. Everything what has to be shipped to the Arctic cruises has to be prepared very much in advance, which also limits some possibilities to last-minute adjustments. There are also other constraints about the instruments. For example, proximity of the magnetic pole. It's a very big challenge for instruments which are using a magnetic compass. There is also a very strong stratification, and as I already mentioned before, a small radius of deformation in the Arctic Ocean, and this requires a high resolution of measurements, which implies a large number of moorings. On the other hand, deployments and operation of ocean moorings in the Arctic areas is very difficult and usually with a much higher risk than in the rest of the world ocean. So you have to find a good balance between the number of the moorings and which is safe and the resolution of your measurements which fulfills requirements to resolve your process or the studied feature. There are different type of moored arrays which have been already used for decades for different applications in the Arctic, and the first type is the moored arrays in the Arctic Ocean gateways. So the places or locations where the Arctic Ocean exchanges waters with the rest of the world ocean. The example of such an gateway array, is a Fram Strait moored array. And this is the moored array which has been located between Greenland and Svalbard in the northern Fram Strait, with between 16 and 18 moorings which were operated by Alfred Wegener Institute from Germany and Norwegian Polar Institute between 1997 and 2012. These moorings were, of course, subsurface moorings with a large float at the top, anchor at the bottom, and instruments which were distributed along the mooring line at 5 different levels, 50 meters below the surface, 250, 750, 1500, and just above the bottom. These moored arrays continued now with a few moorings on the eastern part and a few moorings on the western part of Fram Strait. And another example of moored array which are deployed in the Arctic Ocean, those are moored arrays which were located in the Arctic Ocean boundary current. And such arrays include, for example, the NABOS moored array, the Nansen and Amundsen Basin Observing System, which moorings the line of moorings, or in different years, a different number of moorings, which were deployed in the eastern Eurasian basin at 125 degrees east, with mostly profiling instruments going in the upper 1,000-meter layer. The other example, as shown in the middle, is a Twain moored array, which was deployed since 2012 along the 31 degrees east in the southern Nansen Basin, northeast of Svalbard. This moored array was devoted to measure the Atlantic water inflow to the Arctic Ocean. And that was also the goal of INTAROS moor array, which was a complementary array to the Twain array, which has been deployed since 2017, a little bit upstream of the Twain array at 22 degrees east north of Svalbard, with a different number of moorings in different years. And the examples which I would like to discuss here will mostly come from this INTAROS mooring array as deployed in the last years. The INTAROS mooring included both bottom installations like this mooring frame, and also water column moorings with either profiling or point instruments. The first type of the mooring is the mooring with instruments which are located at fixed depths. For example, this Fram Strait mooring, which I have already shown on the previous slide. This mooring had a steel top float, had an anchor weight, and instruments which were distributed at 5 different levels. The Fram Street mooring, they were deployed at the water depths between 700 and 2,900 meters, but in all cases the instruments were deployed or were placed at the same depths, at the same levels. The other example of the mooring where instruments are located at fixed depths is a deep INTAROS mooring which was deployed in the Nelson Basin. This is a very long mooring which has about 3,500 meter length with the subsurface float, which was equipped with the upward-looking acoustic Doppler current profiler, this Nortec signature, for measuring ocean currents and also sea ice drift and draft, and with very many instruments which were distributed along this 3.5 kilometer of the mooring rope. In the middle we had additional flotation because for this mooring of this length you need to keep it straight, you need much more buoyancy to keep it upright. And in addition to instruments which were located in the float, like this upward-looking current meter, we had over 30 small instruments for measuring temperature and also pressure and conductivity, which serves to calculate salinity of the seawater. And we had also another ADCP, acoustic Doppler current profiler, in the middle of the mooring. This one was upward looking for measuring the currents in the water column. We also had on this mooring several other sensors, which I will come back to a little bit later, the biogeochemical sensors. Another type of a mooring is the profiler mooring. The difference between the previous fixed depths instrument mooring and this one is that here we have the most of the length of the mooring is actually occupied by instrument which is moving up and down the mooring rope. And here we have 2 different examples of moorings which were deployed during INTAROS. The one was deployed at 850 meters, another one was deployed at the water depths of about 1,200. And in both cases we had a top float which was equipped with different instruments for measuring the ocean currents, upward and downward looking acoustic current, Doppler current profilers. And we had double releasers and the anchor at the bottom, but most of the length of both moorings was actually occupied by the neel spin rope, wire rope, and on this rope there was a profiler moving up and down between 2 bumpers. In the case of this shorter mooring, this length of the rope where the profiler was traveling was 760 meters, and for the longer moorings, the profiler was going up and down along the mooring rope lengths of 900 meters. These drawings, they are not up to scale, but if you look at these red numbers and red arrows, this was actually the part which took most of the mooring. There was also some point measurements below and above the profiling instrument, mostly for saving for calibration of the profiler. And also you can see on the right mooring, on the right panel, showing the deeper mooring, and there was another ADCP. This one was downward looking for measuring the ocean currents in the water column. And on the top of in this upper float, there was another acoustic Doppler current profiler for measuring the ocean currents above the mooring, and also sea ice drift and draft. And the last type of the mooring is a bottom frame. We also had this kind of moorings deployed during INTAROS. There was a large bottom frame sitting on the water depths of 500 meters. And the main instrument on this bottom frame was acoustic Doppler current profiler, long ranger, measuring the ocean currents in the water column above the above the frame up to the surface. And there were also smaller instruments located on the frame measuring temperature, salinity, pressure, and also dissolved oxygen. This kind of moorings has this bottom frame also has to be equipped with acoustic releases, so the mooring can be recovered after the releases are open, and the mooring, due to the buoyancy, which is, as you can see, there is a lot of buoyancy located. These orange balls, buoyancy floats, they serve to lift the mooring up to the surface when it is released from the bottom anchor. On the right side, you can see another example of the much smaller bottom mooring, which is an instrument called PICE, Pressure Inverted Echo Sounder, which was used in the Fram Street mortuary. It is a small frame sitting on the bottom with an instrument located in this white ball on the top of the frame, and also attached to the small anchor, which is released, acoustically released during recovery. Let me show you a few examples of instruments which are used on ocean moorings for collecting observations or measurements of physical variables. The simplest type of sensor is a sensor measuring temperature or temperature and depth. And actually the quantity measured is pressure, and the depth is calculated from pressure in all cases for all ocean sensors. And the example of this instrument are seabird sensors SB56 and 39, and also in recent years more used RBR solo instrument, which is an instrument for measuring only temperature, or duet instrument which measures temperature and depth. As you can see, these sensors are very small, they are very easy to handle, and they usually are attached to the mooring rope or mooring wire just with some tape and tie wraps, or with a very simple clamp. More complex, a little bit more demanding sensor is the conductivity, temperature, depth, and dissolved, in some cases, dissolved oxygen sensor. They're called CTD or CTDO sensors. And the most commonly used instrument is seabird SB37, which is also called microcat, and it's a bit bigger brother, seabird SB16, which is called seacat. In the recent years, there have been also more and more used instrument called RBR Concerto, which is the similar type of the sensor. You can see it here on this last photo with a little bit longer clamps. It's a little bit smaller than microcat and seacat. To measure ocean currents, there are two types of current meters. The first type is a point current meter. This is the instrument which measures ocean current only at the fixed level where the instrument is located. In the older times, there were mostly mechanical rotor current meters in use. As you can see on this photo, the current meter was equipped with a mechanical rotor and also with a wing. But they were replaced with time with acoustic current meters, which measured ocean current acoustically. This is the acoustic head for measuring water flow. Both instruments, they were manufactured by Andera, and the RCM 7 or 8 types were the older instruments, and the instruments with the acoustic head were RCM 11 or the newer Seaguard instrument, which is still in use. The other type of instrument for measuring ocean currents is acoustic Doppler current profiler, ADCP. The advantage of this instrument is that it can measure water flow in the entire layer, and the thickness of the layer depends on the frequency of this instrument. The lower the frequencies, the larger or thicker layer can be measured acoustically with ADCP. You can see here different types of acoustic Doppler profiling current meters, for example, from Teledyne RDI, which are the long ranger with a frequency of 75 kilohertz. This instrument can measure water layer which is thick up to even 400 meters. The quartermaster with a higher frequency and then a little bit shorter range for about 300 meters, and the workhorse with the higher frequency and accordingly thinner layer which is measured by the instrument. There are also newer types of IDCPs in use nowadays. For example, Nortec Signature, which is a dual frequency instrument. It can actually swap between measurements with a higher frequency and lower, high resolution, let's say thinner layers, and lower frequency and a thicker layer, which is occupied by measurements. There is also another type of ADCP, Nortec Signature 250, and this instrument has a fifth beam for measuring, which is the altimeter for measuring the sea ice draft, and also sea ice drift can be measured can be measured by 4 beams of this instrument. There are also other instruments devoted to measurements of sea ice, like upward-looking sonars, ULSs, or ice profiling sonars, which are not shown here. In INTAROS, we use a Nortec Signature 250 for measuring ice. In addition to instruments which measure physical variables on ocean moorings, there are also many sensors for biogeochemical measurements and biological observations. Here I would like to show a few examples of instruments which were located on INTAROS BGC mooring deployed north of Svalbard from 2018 to 2019 for 1 year. And this mooring actually carried a suite of BGC instrumentation in addition to instruments for physical measurements. And they included, for example, the Andera Seaguard instrument, which was equipped with the CTD sensor, a dissolved oxygen sensor, but also a turbidity sensor. The other example of biogeochemical measurement was the SAMI sensor SAMI PCO2 sensor for measuring partial pressure of carbon dioxide, or a SUNA V2 sensor for measuring nitrates. There were also clusters of instruments deployed on this mooring, which consisted of combination of different sensors, and this is the example of underwater instrument pack called Octopus, which was developed by Alfred Wegener Institute. And this instrument cluster included underwater vision profiler system, UVP6. This is the optical system for collecting visual images of particles in the water column. But this instrument pack was also equipped with Eco Triplet, the package of sensors for measuring chlorophyll fluorescence, sedum fluorescence, and particle backscatter. On the photo in the upper right, you can see the cluster of instruments, the cage carrying 2 PCO2 instruments, the ADI Seaguard, and then another cage with this SUNA nitrate sensor. Usually these instruments are deployed together to provide complementary measurements of different variables. Another type of instrument, or the sampler actually, which was located on this mooring, was passive contaminant sampler. The small metal frame covered with a special coating for collecting small particles, inorganic particles from the water column during the deployment period. But as I mentioned before, there are not only instruments and sensors on the mooring. There is also mooring hardware and localization equipment. Those elements, they are critical for keeping the mooring in the right position, keeping the mooring tight, and also to enable finding your mooring during recovery. There are different types of buoyancy which are used for subsurface moorings, usually on the top, but also these elements can be distributed along the mooring line. Very common floats are steel floats. You can see them in the top row of photos, these large yellow structures. The steel floats are very heavy but also very strong. They offer a large buoyancy, usually a few hundred kilograms. That means a lot of uplift for a mooring, but they are also depth limited. That means they cannot go down. They cannot go deeper than certain safety depths. Usually, it's a few hundred meters because they may implode. They may implode when they are pulled down. They have a long lifetime and they are very resistant to sea ice when the mooring is recovered in the ice-covered area. The other type of buoyancy which is used on subsurface mooring are syntactic foam spheres or elliptical floats. These shapes, these structures are built of small pressure-resistant glass microspheres combined with larger glass fiber reinforced spheres. All of them are embedded in the kind of the plastic binder, which can be molded to form custom shapes. As you can see in the middle row of photos, they can have a shape of sphere for the double set of instruments, and also elliptical shape, elliptical float for a single instrument. They withstand the full ocean pressure. They can go to larger depths, and they offer the same buoyancy as a string of glass balls, but with considerably less drag, which actually results in the much less of pull down of a mooring. They have medium resistance to sea ice. They are not that fragile, but they still can be damaged when recovered and dragged during recovery through the ice flows. Another very commonly used type of buoyancy are glass balls. Those are glass spheres which are covered with plastic huds. The most common are the glass balls from Bentos or Vitrovex. They offer smaller buoyancy, about 25 kilos. They are relatively light compared to the steel spheres and also even to syntactic spheres. They are very easy to handle. They can be deployed single or also as distributed buoyancy, as packages which are located in different places of your mooring line. But the drawback is that they generate a significant drag, which results again with in a strong mooring pull down. And they can also be very easily damaged during recovery when they are dragged through ice flows. In the recent years, there have been also very special buoyancy floats or buoyancy structures developed and engineered for example, for high current applications. As you can see in this bottom row of photos, this orange structure, which looks a bit like a small submarine, this is a stable mooring buoy, which was specifically designed to reduce drag and also to increase mooring stability in the ocean areas with the extreme currents. It consists of a syntactic foam, which is covered with a protective layer. These special mooring buoys or buoyancy buoys are very large, very heavy, and very capable. But we also have, this is what we have on the top of the mooring or along the mooring line, but we also need something at the end of the mooring, at the bottom. And here we have mooring anchors. As you can see on this bottom row of photos, the mooring anchors in this case are very heavy steel structures, and they can be built from different elements, but very, very commonly used material for for mooring anchors comes actually from railway train wheels. These anchors are sacrificial. That means that during recovery, when the mooring is released, the anchor stays on the bottom. An important component, well, actually critically important for the safety of a mooring, is acoustic release. Underwater acoustic releases are instruments or devices which connect the mooring rope to the anchor, and they can be operated by acoustic commands which are sent from the ship with the transducer which is put into the water. And when the acoustic command is accepted by a release, the hook is opened and the mooring rope is detached from the anchor, and the mooring can actually start to ascend to the surface. Most of acoustic releases, they also offer very important functionality to locate the release by acoustic direction finding. That means that when the acoustic ping is sent to release, it replies back, and from acoustic travel time, you can obtain the range to the releasers. And also, you can most of release. They also provide a release status, which confirms if the hook was open or not. The acoustic releases, which are used for deep ocean moorings, they can carry heavy loads up to 5 tons, and they have a long lifetime, up to 4 years, even longer, which is very important for safety of the mooring recovery. If the mooring could not be, for example, recovered as planned and has to stay another year or 2 in the water. Also, to minimize the risk for the heavy instrumented moorings, the acoustic releases are used in tandem, in pairs, just to provide the possibility of a backup for opening the link between a mooring line and the anchor. Another type of devices which are very important for subsurface moorings are instruments or pingers which are used to localize a mooring, either on a sea surface or also when the mooring is under the ice or still in the ocean. For locating mooring on the surface, when the mooring was already released, and there is instruments which comes to the surface, or the top flotation which comes to the surface, there are usually argon beacons used, or more recently CEO's kilo subsurface iridium beacons. It's a small instrument which sends the signal via iridium and allows to locate the mooring on the sea surface. It provides the position of the mooring. But for the moorings which actually has to be located underwater, for example under the sea ice, if they are recovered from undersea ice locations, this mooring cannot use any solution which works for the surface communication. These moorings has to be equipped with so-called acoustic transponders or pingers, which are interrogated acoustically, and they, in the same way as acoustic releases, they actually reply with the acoustic ping, which allows to get the range to the pinger and to obtain the position for example, from triangulation. For moorings, typically for moorings which are deployed under the ice, there are also avalanche beacons which are located on the top of the moorings, which allow to find a mooring where it comes up to the surface, but to the surface which is covered by sea ice cover, it can be found with the avalanche beacon. Very helpful for locating the mooring on the surface when it is recovered during the night time. It's a flashing light. Usually, it's a strobe light. And also there are radio transmitters, radio beacons which are used on moorings for also to get the location when the mooring top is on the surface. Well, the critical component of any mooring is the line to which the mooring the instruments, the sensors, all sensors, and also other devices which serve, for example, for positioning, are attached. Different moorings use different solutions for this main link, but for deep ocean moorings, and in particular for polar moorings, there are very strong lines used typically for under ice deployments. One example is a needlespin wire rope, which is a galvanized jacketed wire rope, which is construction with socket terminations, and it's very torque and kink resistant. Usually it's 5 to 11 millimeters thick, and it has between 3 and 8 tons breaking strength. It means it's really strong. It can be pulled through the ice without the risk of breaking the rope or the wire rope and lose your instruments. But this needlespin wire rope is also very heavy, and it means that your mooring needs additional buoyancy also for lifting the wire rope weight. There is also another solution which is not wire rope but modern Kevlar or Dyneema ropes. One example which was used, for example, on INTAROS moorings, it was a 12-strand Dyneema, which was thermally pre-stretched and covered with the polyester coat. And these Kevlar Dyneema ropes, they can also come in different thickness. They can be between 6 and 12 millimeters. Well, usually what we use is 8 millimeter Kevlar, 8 millimeter Dyneema, which has approximately 6 ton breaking strength. And what is very important, these Kevlar or Dyneema ropes, they are nearly neutrally buoyant, which means they weigh nothing or nearly nothing in the water, and the mooring doesn't need additional buoyancy to compensate for the rope weight in the water. In critical locations on the mooring, there are also mooring chains used where there is a need for a really strong connection, and also for possibility to attach to the mooring in different places. If we look into specific requirements which are for mooring design, for moorings which are operated in polar waters, in ice-covered waters, I have already mentioned many times that they have to be subsurface moorings. And with subsurface moorings, we have this problem with the mooring line and instruments that they are pulled down by strong ocean currents due to the strong drag which is imposed by large buoyancy elements on the mooring. Therefore, distribution of buoyancy and the shape of the buoyancy which is used on the mooring is actually critical for mooring behavior. But even if we go for these very efficient flotation shapes and flotation structures with a lower drag, designed to provide a lower drag, but there is still a mooring rope or wire which itself has a strong drag and results in a significant kickdown of a mooring. For subsurface moorings, for long moorings which are deployed at larger water depths, the length of the mooring itself is also a very critical factor. Usually, when the mooring is deployed at large water depths, the depth is very often quite uncertain due to the deep echo-sound error. And usually we want to go with the mooring, with the top element of the mooring, as close to the surface as possible, not too close, not to be within the danger of top being damaged by sea ice, but still being relatively close to measure in the subsurface layer. But with this very uncertain water depths, there is a very high risk to make a mistake when you calculate the length of the moorings, the length of the whole instrument, in particular for the moorings which are a few kilometers long. And then there are different approaches how to distribute your buoyancy along the mooring rope or mooring line, in particular for under ice deployments of ocean moorings. For instrument safety, the buoyancy packages should be distributed above each instrument and also above the releases, because if the mooring rope line breaks during recovery, it can be still each element or each segment of the mooring still have enough buoyancy that the instruments can be lifted up to the surface. Or in the worst case, the mooring will come up upside down, and the recovery will be from the bottom end, not from the top end. But on the other hand, for safety of ship operations in the ice, all buoyancy should be actually concentrated on the mooring top. So when the mooring is released, the top float comes to the surface, but the rest of the mooring is actually hanging straight down towards the bottom, and there is no risk. There is no risk to get the mooring rope into the propellers or stuck under the sea ice. So those are these different approaches, and it's sometimes very difficult to decide which one is actually the more beneficial one for the mooring which is to be deployed. These before mentioned requirements for operating moorings in ice-covered waters also imply that a mooring has to be very carefully designed. And there are software packages which can be used for mooring design, for example, commercial packages. But the most commonly used tool for designing ocean moorings in the research applications are the open source tools. For example, the MATLAB toolbox, which is called Mooring Design and Dynamics, MDD, developed by Richard Dewey from Ocean Networks Canada. This software package can be used for designing the mooring and also configuration of the mooring elements. It evaluates the mooring tension and the shape under the influence of ocean current. It can be also ocean current which varies in time. This software can be also used for simulation of towed bodies. And the static model which is used by this toolbox actually predicts the tension and tilt of each mooring component. And it also evaluates the minimum safe mass of the anchor which has to be used for the mooring. These all predictions, they can be saved, then they can be used for the mooring motion correction, and also the currents, which are the time variable currents, can be used to predict the dynamic response. I mean the changing shape of your mooring under the specific current regime. When a mooring has been already carefully designed, the moment comes when it has to be deployed. And there are actually different procedures for mooring deployment, which are used for any mooring, both in open waters and in polar waters, ice-covered waters. The first method to deploy a mooring is so-called deployment anchor last, which usually it's the typical deployment method for open water. But it can be also used in polar waters if there is large enough opening or lid in the ice, which allow to maneuver with the mooring actually pulled behind or towed behind the vessel. The anchor last deployment starts with deploying the top float, and then the following elements are put in the water when the ship is very slowly steaming forward, and the anchor is, as the name says, deployed as the last element of the mooring. This deployment method is very good in terms that it provides less tension on the mooring wire, and is also safer to work for people operating involved in the mooring operation. Also, in good weather conditions, with a calm sea, it can be done without a dedicated mooring winch and dedicated mooring equipment, with a very simple winch, for example, a ship winch. Well, the drawback is that the mooring should be actually very carefully positioned after deployment, because the anchor, when the anchor is actually sinking towards the bottom, it can also drift from the desired location. So the anchor position should be triangulated when the anchor already sits on the bottom. Another method to deploy a mooring, which is actually usually used more often used in polar waters, is the so-called deployment anchor first. When mooring is deployed with this method, the first element which goes into the water is the mooring anchor, and then the whole length of the moorings is slowly lowered down, and the new elements, new segments of the mooring are added one by one during the deployment, when the whole length of the mooring is still hanging on the crane or on the winch on the ship. To do deployments anchor first, the ship has to be equipped with mooring winches. They can be permanently installed mooring winches, or also mobile mooring winches. You can see the two examples on the right photos here on the slide. But also there is a large tension on the mooring wire because not all buoyancy is actually already in the water when the mooring is lowered. Which actually means the larger risk for people working with the mooring on deck. The advantage of this deployment method is that this deployment can be done in relatively small leads and openings in the sea ice, because ship has to be stationary with the lead, and mooring is lowered within the opening, drifting together with the vessel. If the position during deployment is stable, if there is not much drift, then the mooring or anchor of the mooring can be actually put on the bottom and then released. So there is no additional need for positioning, because the position is known from the vessel position. When the mooring has already spent a year or two in the water and collecting measurements, it has to be finally recovered. And recovery procedures in the polar areas, in the ice-covered waters, they are linked to additional challenges as compared to open waters, which are related to the presence of the sea ice. The standard sequence for mooring recovery is to position, to release, and then to recover a mooring. And in the case of moorings in the ice-covered areas, the positioning of the mooring is even more critical. The minimum activity before recovery is to position the anchor, to obtain the very accurate location of the mooring. And very helpful. It is very helpful also to position the top of the mooring, the top transponder, which is located at the top float, because in the case of very long moorings and under the strong ocean current, the mooring actually can deviate from the vertical, and the position of the top element can be quite different from the position of the anchor. And very often there is only a very small opening when the mooring can come to the surface and be recovered. So the position of the top element is, knowing the position of the top element is very, very important. There is also a very important aspect to secure enough time for proper ice management before releasing the mooring. Very often there is, especially in particular if there is a strong wind or strong current or both, and the ice conditions are changing very fast in the mooring location, there is only very short time window when the opening, which was artificially made by icebreaker, can actually move over the top of the mooring, and the mooring can come to the surface and be recovered. And the difficult task is to actually to estimate the time which is needed for the mooring to reach the surface. It's less problem for the moorings which are subsurface moorings, which have these top elements 20 or 30 meters or so under the surface, because they come to the surface relatively fast. But for moorings which have top element located much deeper, or for example for the bottom frames, which are just sitting on the bottom, the time needed for the mooring to reach the surface is much longer. And during this time, the mooring or the frame can actually drift significantly from the deployment position. So it can even surface under the ice, which is a big problem for these bottom moorings. Then it is again very important that these moorings are equipped with efficient and reliable acoustic pingers, which allow to locate the mooring under the ice or still in the water when it is drifting. Well, even if the mooring top comes to the surface in the small lid in the open water, there is usually very fast ice drift, and the remaining part of the mooring usually, even if the top of the mooring comes to the surface in the open water, the remaining part very often is actually dragged. It comes up under the ice and has to be dragged from below the ice. So the time is also a very key to successful recovery. If the longer the mooring stays in the water after releasing, the bigger the risk that it will get stuck under the ice and has to be dragged through the ice flows. And there is a large risk to damage the instruments or even break the mooring rope or wire and lose part of the moorings. Well, if there are acoustic transponders located at different part of the moorings, they can be used, even if the mooring breaks, they can be used to find the mooring elements, even if they are under the ice, or even if they didn't come to the surface. They can be even dredged from the water if needed. But these dredging operations are for the moorings which were not able to fully surface, are much more difficult in the ice if not impossible, very most often impossible in the ice-covered waters. So the recovery really depends on many factors, and also depends on the way how the mooring was designed and how well it is equipped with additional devices which allow to find the mooring under the ice or in the water. One of the biggest problems with subsurface moorings in the polar areas in ice-covered waters is the lack of surface element or surface expression of the mooring. And without this surface buoy, there is no way to, for example, to send the data in real time using, for example, a satellite link to the land station, which would increase the safety of the data retrieval and also would enable to use the data in the operational mode if they are retrieved in real time. Without surface element, there is also no way to collect the data in the uppermost layer of the ocean, the layer which is very important in the Arctic Ocean. There were some technical solutions already proposed, developed and partially implemented in different mooring arrays in the Arctic. And for example, on the left side, you can see example of the acoustic data telemetry system, which was based on acoustic data telemetry between moorings located in the eastern part of Fram Strait, which were connected acoustically to the independent central mooring, which was equipped with the underwater winch, with the profiler. And the idea was to collect the data from these neighboring moorings in one central unit and then send them as a small data packages via this underwater profiler, underwater winch with the profiler, which actually ascend to the surface once a day or every second day. Here on the lower photo, you can see the example of the acoustic modem, which was used to send the data between moorings. There are also other systems which were designed to provide the surface access and subsurface measurements for single moorings deployed in ice-covered waters. For example, on the left side, you can see underwater winch with CTD profiler, and the profiler was also equipped with a satellite iridium modem. And this modem was used, the profiler was also rising to the surface once or twice a day and sending the data which were collected both by profiler and by the instrument below the winch to the land station. Another solution which was used in Davis Strait, that was so-called ice sacrificial moorings, so-called IceCat, which consisted of a small profiler or small instrument which was located just under the ice, and it was connected to the main mooring by a weak link. But also there was a link for data transmission to the main mooring, and when this small profiler, small instrument was lost, the data which were collected, they were still in the main logger, which was at the main mooring lengths. Another instrument which was used to provide subsurface measurements from under the ice was so-called ice cycler, which was another kind of the mooring profiler, which was energy conserving profiler to measure under the mobile ice cover, which was used in the Canadian Arctic archipelago straits by Canadian partners. The good example of the system, of the future system, providing integrated measurements, integrated observations from different platforms is FRAM. It's a Frontiers in Arctic Marine Monitoring System operated by Alfred Wegener Institute from Germany in Fram Strait. And this is example of multi-platform and multidisciplinary observing a system which consists of these fixed platforms, ocean moorings, subsurface moorings, as you can see on these graphics, which are partially equipped with the underwater winches, with the profilers, and with the profilers they can reach the surface at least periodically. And also data can be harvested from the mooring instrument, from subsurface mooring instruments, for example, by underwater autonomous vehicles like gliders or AUVs. So for future, there are new technologies and new instruments, new solutions which are needed to improve and extend mooring operations in polar waters under the sea ice cover. So let me summarize everything what has been discussed during this webinar. The oceanographic moorings are bottom anchored lines which are kept tight by top buoyant float, and they carry a collection of autonomous sensors which are distributed along the mooring lines. And due to ice cover, moorings in the polar waters never reach up to the surface. They are always surface moorings. Moored instruments, they measure seawater properties and also water movement at fixed locations, providing Eulerian measurements. And there is a large variety of different sensors which can be used to measure physical variables like temperature, salinity or ocean currents, and also biogeochemical variables, including dissolved oxygen, nitrates, pH, PCO2, and many other parameters. The same sensors can be used on moorings deployed in polar areas as on moorings in open waters, but they have to be capable to operate in cold waters, actually, and the sensors and instruments have to be robust enough to survive operations, means deployments and recoveries in ice if it's needed, and usually it is needed. Due to the difficult access to polar areas, the moorings are deployed there for longer periods, and they are turned around once every year or every second year. And this implies that larger capacity of batteries is actually needed for autonomous instruments. And also the sampling schedules, they have to be very carefully planned for these longer periods. The subsurface moorings, they have to be equipped with acoustic releases, which allow to release the mooring from the anchor, and also they allow positioning of the anchor. And in ice cover areas, mooring have to be carefully positioned before releasing, and they also should carry additional devices for acoustic localizations like pingers, in the case if the mooring comes to the surface under larger ice flows. It is very important to plan carefully ice management before releasing the moorings. This is very often the key to the successful recovery, and the critical requirement for that is a good cooperation with the ship navigators, officers, which is absolutely necessary. And also, mooring design is a critical issue. Know your moorings. Plan the different possibilities and requirements for deployment and recovery depending on the vessel which will be used, and taking into account that the mooring can be or probably will be recovered from under the ice. So this has to be already taken into account at the design phase when it comes to the distribution of buoyancy to these different devices for underwater and under ice positioning, and other aspects of the mooring design. And in future belongs to ocean observatories that actually comprise of very different platforms, or fixed platforms, moorings, and also the mobile devices and vehicles, which can be also used in combination with moorings. So it is very important to include new technologies on the moorings which are deployed in polar areas that will also allow interoperability between different platforms. And the example is to use moorings or AUVs, for example, for harvesting the data from subsurface moorings. And with this remark, I would like to thank you for your attention and wish you a lot of success in designing, deploying, and recovering of your moorings in the polar areas, in the ice-covered waters. Thank you.